Hello everyone and welcome to this webinar. Our title today is the Introduction to Tenstorrent Grayskull Acceleration AI Inference. My name is Yassine Hariri. I am Senior Scientist at CMC Microsystem. My space of expertise is AI and ML. And I have the pleasure to present our guest speaker today, Tom Stesko, Staff Field Application Engineer from Tenstorrent. So this webinar will be recorded and the recording will be available afterward. So the agenda of our webinar today, we will cover the following items. First of all, I will give a high-level introduction of CMC microsystems and our edge AI solutions. Tom will present the Grayskull e150. He will cover the hardware architecture as well as features and specification. Part of the presentation will be how to use the available software stack from Tenstorrent in order to facilitate the use of these AI accelerators. This also includes firmware, AI model compilers, then we'll present some use cases for this platform. We will conclude with a demonstration on how to access the server hosting this AI accelerator board from CMC Microsystems, and we will conclude with a Q&A session. So high-level introduction of CMC Microsystems. We are not-for-profit, founded in 1984, enabling innovation in a network involving more than 10,000 academic participants and industry as well. Our main mission is to provide services to simplify access and reduce cost to advanced technologies, including microelectronics, photonics, IoT and edge AI, MEMS, nanofabrication and integration, and quantum technologies. Our independence from any specific application means that our services are equally valuable and to those engaged in advanced manufacturing, clean tech, agriculture, health, and beyond. And we offer the necessary infrastructure and work to reduce the barrier to the adoption of cutting-edge technologies and empowering our client to conduct their research and development with greater ease and efficiency. We are proud to be part of a Canada-wide collaboration between 68 universities, colleges, connecting 10,000 academic participants with over 1,000 companies to design, make, and test micro and nanosystem technologies. We offer our products and services under 3 banners: CAD, Fab, and Lab. CAD consists of state-of-the-art software for successful design. Fab, by simplifying access and reducing cost for working prototype. And Lab consists of lab for test and demonstration of these prototypes. So the latest project that CMC is working on is a proposed 5 years, $200 million project, and the main objective here to build its first of its kind national ecosystem to create critically needed semiconductor capabilities in Canada. So it's one project with 5 activities. The first one is to create capacity for fabrication of semiconductor devices in Canada, accelerate R&D of IoT products and services by SMEs operating in all verticals, develop the skills needed by industry, take quantum technology to market, and grow the Canada ecosystems in semiconductors. So this is an exciting project, and you will hear some news very soon about the progress. So this part of the presentation is a very brief. It's summarize our products and services in supporting edge AI developments. So it's a one-stop shop for edge AI, and we help our clients to enable them from the conceptualization to that data management, their model training, model optimization, inference, and development. This slide summarizes our products and services in the space of edge AI, and this is in collaboration with our partners. We offer a leading edge infrastructure to enable our clients, including the researchers and SMEs, to train their models in our cloud infrastructures, which is composed of dedicated neural processor or custom accelerators for AI training, GPUs and FPGAs, We support a wide range of software stacks for and frameworks to develop deep learning models, including TensorFlow, PyTorch, and beyond. On the inference side, we partner with two leading-edge companies here in Canada, the Tether AI, and today we have the Tenstorrent presentation. They both offer leading-edge accelerators to researchers and industry to accelerate their inference at the edge and in the cloud. We are also part of a large ecosystems of RISC-V. We are partnered with Open Hardware Group, and we are leading few project collaboration between industry and academia. So to learn more about these infrastructures and the opportunities, you can visit cmc.ca/edgeai. So before I give the hand to Tom to present his presentation, I would like to announce the upcoming workshop. So annually we organize a workshop completely dedicated to accelerating AI. And the title is Challenges and Opportunities in Cloud and Edge Computing. We have a very exciting agenda for next week. So for researchers from industry and academia sharing their latest innovation in this space, I encourage you to attend this one. And this is a snapshot of the high level of the agenda. So how presentations from Synopsys, Tenstorrent, NVIDIA, Open Hardware Group, Tether AI, ARM, and from academia, University of Waterloo, University of Toronto, and McGill universities. And these are very exciting talks. So I encourage everyone to attend those. And if you have any questions, you can go to CMC website and register or ask any questions. The last slide is the discussion group that we are maintaining at CMC. It's called Accelerator AI Systems. You can join the group to get the latest news about the event as well as the training held by CMC. So I stop here and I will give Tom the time to present the Grayskull technology from Tenstorrent. And after that, I will provide a quick demo. Tom, I will end share and you can share your screen.
Super. Thanks, Yassine. Let me put up some slides. All right. Can you see my screen here?
Yes.
Yeah, so I'm really excited for this partnership with CMC. So as Yassine mentioned, we've got two E150 cards on a CMC server available for people to use. So I'm going to be showing you today how you can kind of get started with that and what you can do with it. And this is a really interesting dev kit. So the Grayskull e150 is a dev kit for Inference. So without further ado, I'll get started. I'll go through these slides and then do a hands-on demo on a similar server with E150. Okay, cool. So let's start by talking, what is Tenstorrent? So Tenstorrent is an engineering design company. So we build computers for AI and what we're calling the first mass-produced graph computer. So that's kind of a combination of general compute and AI accelerators. So I'm going to be talking about the AI accelerator part today with the first generally available version is the Grayskull. So that's utilizing our AI 10.6 cores. And I'll talk about our open software, the BUDA and Metalium stack that enable seamless scaling. So really we're using commodity Ethernet technology to scale. And that allows you to remove a lot of switches, routers, and the dependency on host computers and expensive high bandwidth memory. And this is using a data flow architecture. I'll talk more about what that looks like. The other piece is also RISC-V high performance CPU design. So we're bringing the two together. Today, I'm really just going to be talking about the AI 10.6, but both together is a very exciting story. Okay, so why should we care about this now? Why not wait a year? Why not wait a month? So the answer to that is really about the momentum that we're building, and especially the momentum in our developer ecosystem. So we really believe in open standards. We're putting out as much of our software as we can, nearing 100% of our software open source. So we have our low-level TT-Metalium stack open source back in December, and that's kind of our kernel programming environment. So you can start from really the bare metal, writing C++ kernels and kind of build up from there. Then we launched our Grayskull DevKit back in January. So you can go to our website today, you can buy a card, and it will be shipped to you. And it's kind of priced really so that no one is pushed out of the market here. We want to make sure that as many developers as possible are able to get their hands on this. So there's an E150 and an E75 model. And the last piece is TT-BUDA. So that's our top-down compiler stack. And this allows you to take existing models that were developed in something like PyTorch and then have it automatically compile down so it runs on our device. So again, we're trying to make it as easy as possible to program on our hardware and make this platform available to people. Okay, so let's jump in and look at what Grayskull actually is. So here's kind of a zoom in on the Grayskull chip, and you can see there's a grid of 10 by 12 cores. So these are the 10.6 cores. Each T here is one core. And I've kind of blown it up here so we can look at the innards of the 10.6 core. You've got 5 baby RISC-V processors. And these are really driving the computation on the device, really from the memory side. So one RISC-V core is effectively driving one NOC, network on chip router edge. And this is going to allow you to move data in and out of L1 memory. So the second RISC-V processor can move data out of L1 into dedicated compute hardware. So this is kind of the math engine, if you will. And there's specialized hardware for matrix and vector operations. The third innermost RISC-V processor is running dispatch to the dedicated hardware here. And then the last two kind of do the reverse of the first two. So you can move data out of the dedicated compute engine into L1 and then through back onto the NOC edges. On the boards, we also have DRAM. So for Grayskull, it's LPDDR4, and you've got 8 channels, 1 GB each. You also have PCIe and ARC system management processor. So we can look at our current PCI cards that are available. So the first two are part of the Grayskull DevKit release. And these have, specifically for the E150, 120 cores, like I mentioned. And that's 1 megabyte of SRAM per core. So the memory is spatially distributed across the chip. One of the key differences between our Grayskull and Wormhole chips is the DRAM. So you're seeing here increasing capacity. There's also increasing capacity on our SRAM per core, so it's 1.5 megabytes for Wormhole. And then nearly 3 times the DRAM bandwidth from Grayskull to Wormhole. Probably the biggest difference, though, is the introduction of Ethernet. So we have 16 lanes of 100 gigabit Ethernet on the Wormhole boards. And this allows you to scale out. So you can interconnect different boards and different chips and kind of create that sea of cores, if you will. Okay, so I'll showcase kind of a few views of our software stack. So we'll go through this a couple times, but kind of going up from the hardware. So you have a host CPU and some Tenstorrent hardware, and you can imagine the firmware is on the hardware. Then we have a kernel mode driver, a user mode driver, and then you get either a low-level programming environment in C++, the host API to drive those kernels. And then on top of that, our engineering team developed some intermediate abstractions for neural networks, for BLAS, collective communications, and these are kind of ways to build up to something like a PyTorch experience. The other way of looking at it is the top-down approach. So you can look at existing PyTorch or say JAX model. Then we use Tensor Virtual Machine, Apache open source project to compile down and run specific binaries for our hardware. I'll give you another view of that. So kind of what I mentioned now with Metalium is you have the ability to write kernels for every single one of those baby RISC-V processors in each core. You can address every register on the device, so the hardware is completely programmable. And this is kind of that data flow that I mentioned with reader kernel, reading from one router edge on the NOC, pushing data through to L1 to the dedicated math engine, if you will. You can write a matmul kernel, and you can specify then where that memory is going to go. So it's going to push it out of L1 to the router and then to, say, an adjacent core. Then we've got another view of the BUDA stack. So starting from, say, PyTorch, Tensor Virtual Machine, then we can lower to actual Tenstorrent implementation of a kernel. So this also allows us to do operator fusing and erasing. For example, you could have a tensor manipulation like a transpose that can be implemented with just changing in the NOC where the input and output of adjacent core memory transfer happens. So it doesn't actually need to be an operator. We also have AutoGrad for training. Specifically for Grayskull, we don't support training. That's on future hardware. But this gives us the backward pass and the gradients and intermediates. So then we run an optimization problem to parallelize all the different operators across different cores. And then we have those hardware-specific binaries and the backend engine to schedule and run them on the device. Okay, so hopefully I can explain this well, because this is a complicated topic. But one of the key models we have is not just a temporal, not just a spatial, but this hybrid spatial temporal execution. So this allows us and the programmer really to use the trade-offs between temporal execution and spatial execution to their benefit. All right, so what is temporal execution? So that's probably what you would be familiar with something like a CPU or a GPU, where you have potentially many cores, but every single core is running the same operator at the same time. So they're all running in sequence. And then that creates a very high dependency on DRAM, because after every single operator, you need to write out all the intermediate data. You need to get the new binaries for the next operator to run. So you can kind of solve this with a spatial execution model, where you can have multiple operators running on the same chip on different cores. However, that creates another problem with the so-called pipeline fill and drain, or essentially bubbles in the process. So if you're running inference on a batch, you're going to run from one edge of the chip to another. The very last operator initially is going to be empty. So it's starved for data. It doesn't have any inputs, so it's idle. And then at the very end, that final operator is going to be running, but the initial operator is also starved for data. So there's two trade-offs here that we're really trying to tune for specific models. And that gives us this concept of an epoch, which is an overloaded term to be sure with machine learning. But an epoch here is really just one instance of all the operators running on a chip simultaneously. So we're going to run multiple epochs, so multiple instances of what's running on a chip. And again, tuning for that trade-off between the pipeline fill and drain in spatial and the DRAM bandwidth problem in temporal execution. Okay, I'm just going to talk briefly about the software ecosystem and support, how we're doing that today. As I mentioned, we really believe in open standards and open source, so we've got all of our software up on GitHub. We also release Docker containers. So this is something you'll get with the stable releases of TT-BUDA. We have our documentation website, and we have Discord for community support. So you can ask questions there, get answers, and talk about your projects. And I'm really hoping that people are happy discussing projects there. I'd love to hear about the really cool stuff you're doing with our hardware. And then finally, if you have any other questions that you want to address in private, feel free to drop us a line at support@tenstorrent.com. Okay, so I'm going to start the live demo portion of this. So I'm going to stop sharing and I'm going to switch to another screen. All right, so you should be able to see my screen here. Please let me know if the font is too small. I know it can be a struggle if the resolution isn't coming through. Okay, so I have this repo here, CMC TT dev infra, and I have this little script, so I can make that available for you later, but this is kind of an abstract of what we're going to do in this demo. So Yassine mentioned he's going to go through how to actually access the CMC server using CAD-Pass, and he has a really great guide for that down here. I'm going to also show you how to use Docker with our cards. We're going to run some models with TT-BUDA. We can actually look at the compute graph and the placement with a tool called Reportify. So this isn't actually open source yet, but if you need it, I can find a way to make it available for you. We also have a way to compile ahead of time and actually save those artifacts in a so-called TTI or Tenstorrent image file. So that's really useful for production applications. We're also going to look at how do you benchmark model performance and accuracy and show you running loops over batch inference. We also have a performance tool called Perf Analyzer. So I'll show you how to use that. And we'll look at some of the overrides and configurations you can provide with TT-BUDA compiler, which is the Python interface of TT-BUDA. So first, I'm just going to direct you to our software utilities. So this is kind of the low-level software, if you will, the firmware, the drivers, and the system management interface. Okay, so I can show you TT-SMI here. So it's a command line tool that gives you this nice little UI that you can use to look at connected devices. So you see we have device 0 here. That's our E150. You'll see the driver information. So we're at 1.27.1. We also have host information, memory, etc. You can also look at the firmware version, and you can see telemetry from our hardware. So you can see the temperatures, power, the clock speed, etc. So the device right now is idle. And then finally, one important thing with TT-SMI is it allows you to reset the card. So for whatever reason, if you do not shut down the card correctly or you have a bad memory state, you will have to reset the card to be able to run models again. And this is less of an issue with future generations, but with Grayskull, it's important to keep in mind. Okay. So I have opened here our script, and let's look at first our BUDA demos. So I'm going to clone our repository here. And I'm actually going to start running our Docker container. So you can pull it directly from GitHub, the container registry. I already have the Docker image. And then I'll go through these Docker run options. This is a good way to get a stable containerized environment. I will call out that we're using a root user here, and we're also adding the Linux capabilities, which is super permissive. So this is okay for a demo, and this is not connected to the internet really. This is over SSH. But if you were going to use a production application, you would want a more feature-rich container that has better security and provisioning. Another important piece here is how we're mounting our hardware. So we're mounting from /dev/tenstorrent0 to the same inside the container. It's important to make sure if you're using a single card, you want to have the mount point be /0 inside the container because that's what the software would expect. I'm using the huge pages 1G, so we bumped up the default huge page size, and that's an operating system feature. Similar to shared memory, it's going to allow us to have faster large data contiguous reads and writes. So that's important for some large ML model and large data sets that we're going to be using. So I'm going to mount our demo volume so that we have our persistent file storage. And then we have this testify volume. So this is just the default location for some diagnostics that I'm able to render with Reportify. And I'm just going to grab some extra system dependencies. So just git and rsync so I can get more code. And then the first thing I'm going to do is I'm just going to run PyTorch ResNet, and I'll step through the code of how that works. So you can see here in model demos all the different implementations we have. Then we have different implementations for, say, Onyx and PyTorch. Here's the PyTorch version. So we're able to take the model direct from Hugging Face, so the original implementation from Microsoft of ResNet 50. We're using the transformers library. And what we're actually doing is we first set some compiler configs. So we can set say a balancer policy, which is kind of like the initial algorithm to set, say, the initial solution before the optimizer completes it. Then we have an image that we're going to run. So this tiger here. And this line here is the most important. This is where we're actually going to create our PyTorch module. So we pass in the entire PyTorch compute graph. We pass in the inputs as well. And this is going to compile and run inference all in one. So when we get the output queue and we call .get, that's when we start to compile and run. And then we can get our predicted value. So you can see here what we actually printed out. So the true label was a tiger, and we predicted a tiger. So we can see that the model is indeed running correctly. All right, so the next thing we can do is look at the placement. So here on the right-hand side, I've got our Reportify app running. We can see for ResNet 50, placement, initial graph, and post placer. So the initial graph is what TVM would have seen. So this is the entire compute graph. And you can imagine, like, this is a small model. ResNet 50 is not big. So a large model is going to have either much bigger ops, or it's going to have, a much longer compute graph. So it's already hard to manually look through. Here with the post placer, we're going to see what our optimization on the device actually gave us. So you can see the actual epochs are broken out now. And I'll give you a better view of that in the placement graph. But you can also see some operators are fused together, like this one. And I'll show you the placement. So this is actually an overlay over our 10 by 12 grid of cores. So you can see all the actual operators in a given epoch. And what you'll tend to find is starting from the banks of DRAM up here, so you see all 8 banks of DRAM, you have a lot of the operators at one edge are going to be reading in data from DRAM. And then you're going to see a lot of these operators only have dependencies and input data from other operators, not from DRAM. So the inputs are the red lines here, and the outputs are the blue lines. And as you get to the other edge of the chip, you're going to see a lot of these operators are outputting to DRAM, so they can be read in the next epoch. Okay, great. So let's look at a more complicated example. So now I'm going to show you our benchmarking repository. And while the requirements are installing here, I'm going to open up the code. So I'll also mention that this is another open source repo and is really great for customers because the first thing that our customers want to do often is run benchmarks. And we want to enable that. So you can see here, and we kind of have releases of this along with our TT-BUDA releases. So what we're going to do is run with the Tenstorrent image files. I'm going to showcase how to use that, and I'll step through the code to show you specifically how the implementation works. First, I think I have to log in. To Hugging Face. So this is kind of like the first run experience that you'll get the first time you run through this repo. So I'd encourage you to look at some of these implementations. We have all the different models that we have benchmarking implementations for here. And each one of these has a bunch of different variants. So you'll see we have the base and large version of VIT. So I just downloaded the base version here, and we're going to start compiling for the Tenstorrent image file. And I'll show you also we can use specific tasks for evaluation. So the vision transformer we're evaluating for image classification, which means that we have the specific Hugging Face transformers model implementation from PyTorch. We also have the standard ImageNet 1K validation dataset. So we are going to be using the standard validation to determine is this model working correctly, and we can compare it with CPU, GPU, or other accelerators to make sure that the implementation is correct. So we're going to use a standard accuracy evaluation metric. And now I'm going to show you the benchmarking script itself and how it drives the actual model run. So don't worry about all this code. I'm just going to show you a few lines. So if jump down here, these lines in particular show kind of the switch between the load TTI and save TTI, or if we're doing compile and run all in one. So for load TTI, we can actually take an existing TTI image from a path, create this TT-BUDA TT device image object, and then we actually load that to create the TT device object. Alternatively, we can create that TT device object direct from a model implementation. So this would be the PyTorch model itself, and then we pass in some details. So for example, we would pass in chip 0 and the Grayskull architecture, and that would create our TT-BUDA device object. So next, we can go down and look at how we would start the compile. So here, this TT-BUDA.initialize pipeline will take specifically sample inputs and either, well, for training, you would also need to pass in the sample targets. Here, training is false, and this is empty. The targets are 0 because we're only doing for inference. And this gives us our output queue. So then finally, we can go down and look at how the inference loop works. So this is kind of the simpler inference loop right here. And this is really just going to go through a number of counts. And it's going to take from the input data each batch of inputs and run it through the forward pass of the model. We also pass in the output queue in the device, and we pop off from that output queue our output and then store it in a list. So that's kind of the simplest way you can think about the batch inference working. And I'm going to start doing that inference loop with now loading the TTI image. Actually, let me show you the TTI image. So we just created this TTI, and that's 546 megabytes. So again, that's the entire weights of the model and the compiled binaries to run on the Grayskull chip. So now we're just gonna kick off this inference loop. I'll also mention down here there's an asynchronous implementation that allows you to have the input thread and output thread be separate. So this can help reduce some of the overhead of pushing and popping from the output queue, and in most cases we kind of reduce that by doing all the pre and post processing outside of the main loop. But this can be a slightly more optimal implementation for some models. Okay, so we just loaded that device image here. So the device image contains some information about the TT-BUDA version. We can even see the commit SHA, and then some information about the Grayskull device. So this is, what input shape it was compiled with, the grid size, and the type of silicon. Okay, so we should see it start doing the inference loop now. And then we're going to get some output statistics. Great, I already finished. So you can see the compile time is still not nothing. This is mostly just for loading the image, but it's much faster than having to do the full compile every single time you want to run inference. We also see some information about the peak memory usage, the number of samples processed. You can see the samples per second and the evaluation score. There's a bunch of other metadata here about the TT-BUDA version, etc. So I just want to mention that when it comes to performance, this is improving week over week. Yeah, if we go back, we can look at the releases for TT-BUDA. And you'll see even in the release notes every couple weeks. So we have alpha releases and stable releases, and you'll be able to see in the notes that we're still adding a lot of new features, we're adding new models, and we're improving performance pretty significantly on each release. So this is, again, why we want to enable our customers to do kind of continuous benchmarking, so you can actually see these performances and actually get them and use them in your production applications and for your testing. So we can also look at our VIT placement, just to give you an example. So this is a much larger model. So we're going to have a lot more epochs. Yeah, so I think there's like 32 epochs. And again, if we think about that trade-off between spatial and temporal execution, you can imagine, like, if every single one of these operators had to run on its own epoch, you'd have, obviously hundreds, if not thousands of epochs. So we do get some economization there on how we're effectively utilizing our spatial architecture. And again, we can see a lot of these initial operators reading in from DRAM, and then writing out on the other side. All right, so the next thing I want to go to is using perf analyzer. So there's a really good guide in our documentation here. So I'm just going to step through how to use it. So for that, I'm going to go back to our TT-BUDA demos. I'm going to turn on these environment variables. And it's important to kind of think about when you're doing this. You can't do this all the time because it does add quite a bit of overhead. But I'm going to start the run here, and then we can look at the performance data. So Perf Analyzer is a terminal app, and it's going to kind of give us estimates and measurements of cycle times of every single operator. And you can use Reportify, either the placement diagram or the post-placement graph to kind of help you hone in on why some of these operators may or may not be bottlenecking. And you can kind of reason about, okay, which operators might want to be increased in size or somehow changed. So we're going to see here when the graph runs the output data, and then I'll be able to save the data from Perf Analyzer into a binary file so we can look at it later. Okay, that just finished. Right, so we can load in this binary file. And I should mention, so you see on this path here, the tool is called perfanalysis.py, and this is actually built into the TT-BUDA release. So you should be able to use this anywhere that you have TT-BUDA installed. So we're passing in this netlist as well. And I can show you very briefly what the netlist looks like. It's kind of hard to look at just on its own, but is kind of an interesting artifact. Actually, yeah, this might be pointing to a temporary file. Yeah, I'll just continue here looking at the epoch summary with perf analyzer. So what this is showing us here is per epoch. So we've got the 6 epochs. It's showing us the slowest operator on every single epoch. So we can look at here this as the bottleneck, so add 112. We can open up the stats for this epoch, so this is epoch 0. We can also look at, here we have an estimate of the total samples per second. And you can get that per epoch as well. And you can imagine that the total is just kind of going through every single epoch and the speed that you get after that. Yeah, so using this little terminal application, we can see this BW kernel, or the bandwidth kernel, is kind of the most important stat, and this is the measured number of cycles it takes to complete this operation. So you can see we can actually automatically, with the logic of perf analyzer, already describe some of the problems that it has. So why is this operator bottlenecking? And in this case, it's the output. So it's writing a lot to DRAM, and that creates a bottleneck. Right. So we can think about how do you improve this, and just to kind of cheat a bit, and for the sake of time, I'm going to show you, we actually have a different implementation, or I should say different configuration override of ResNet in the benchmarking repo. So this kind of represents our current engineering team's best guess at what is going to give us the most performance for these models. So we can actually copy this over to the version that we are running. So I'm just going to use these configurations so we can look at what the difference is. So these are the configurations we had. Now I'm going to add these ones. And I'll just simplify this because I only need the configurations for Grayskull. Okay, great. So now I can run the model again with the diagnostic data collection enabled. And this is going to create the outputs we need for perf analyzer. And then we can compare the difference between the first run and the optimized run with the new configurations. So one other thing I'll mention is we have, when it comes to the overrides and compiler config, we have documentation on the compiler configs. So all of these different options. So these are available in the documentation, and there is quite a lot of it, so I encourage you to look through it, especially when you're trying to figure out why you may or may not want a given configuration. For the overrides, we have this more coupled with the code base. So this is in the TT-BUDA open source repository. We have all of the overrides listed here and kind of a brief summary of what they're doing. Okay, great. So we just finished that run, so we should be able to save. Here, I'm going to save it as V2. And I'm going to load back the performance data. Okay, so now we see, okay, there's now a larger estimated samples per second, but we have more epochs. So that's kind of interesting. So as I was mentioning, with the trade-off between the spatial and temporal execution, sometimes it does make sense to have larger operators on a given epoch, driving you to have more epochs. So we can actually look at this in Reportify now. So if I open up the new placement, we're going to see those 10 epochs.
Tom,
Yep.
there is a question in the chat.
Oh, great.
Can you define an epoch?
Yeah. So it's an overloaded term. An epoch in our sense is really just, say, this example here. It's one instance of all the operators running on the chip, or a set of chips if you're running with multi-chip. So you're going to schedule all of these binaries. So here we have 12 different operators, so 12 different, each core is going to get the binaries for that operator. And then it's reading in from DRAM and then writing out to DRAM between the epochs. So I hope that clarifies what an epoch is. I know the nomenclature is a little bit tricky because epoch in the ML context is kind of one loop over the training data set. And we are overloading that term. But if you'll bear with me, I hope it makes some sense in that it's kind of one loop, if you will, over all the binaries in one instance of the chip running.
So it's a cycle from DRAM to compute to DRAM atomic operation.
Yeah, it gets a little bit trickier because we have something called T-streaming, which allows you to kind of cycle through an operator multiple times. And this is kind of important when you're looking at, well, some operators are going to be much larger than other ones. So if we look here, like here in Epoch 0, I'll try to open this over. So we can see like some, this operator is going to be much larger than this one.
Yeah. What about we unmute all the participants and we can allow them to ask questions directly?
Yeah, please.
So Brent, if you can do that, but there is another question in the chat from Raul, who initially asked a question about the Epoch. So are the DRAMs assumed to be connected to all DRAMs? So I think it's the hardware architecture of the chip. So is there a direct link there, or?
Do you mean DRAMs are all cores able to read from DRAM, or is the DRAM? I'm not sure what you mean by DRAM connected to DRAM.
Yeah, I think Raul, are you able to unmute yourself and ask the question directly?
Can you hear me?
Yeah.
Yes. Yeah, go ahead.
I know. I'm just trying to understand the underlying architecture. So you have, looks like you have heterogeneous cores that need to be scheduled in some interesting way, and then you have inputs and outputs that go into DRAM. I'm trying to understand how the DRAMs connect to each other. So is there a architecture or nearest neighbor, or are they? Is there sort of a central point? Are there networking resources? I'm just trying to understand what the interconnect fabric actually looks like.
Yeah, so I think I understand your question now. So you're talking about each one core connecting to another core on the chip. So that's over the network on chip, which is very similar to Ethernet. So there's kind of two network on chip dimensions. So there's kind of an X and Y to it. So every core can read and write to other cores, and that's all in SRAM. So we have those router edges on each core. And again, I can send data, let's say, from this core to an adjacent core. So you'll see like this core here, or this operator, each of the cores is actually reading from the adjacent core.
Right. Okay, and then the DRAMs are, what's the connection of the DRAMs to each other and then to the cores?
Yeah, so the DRAMs are connected to the core. So every core can also read from DRAM. Obviously, the DRAM is much slower, especially on Grayskull. So you really only want to use that to kind of initialize the epoch. And in this case, a lot of these operators are reading themselves from DRAM. And that's kind of how you get around the...
So all DRAMs, so even though this sort of shows it, even though this shows kind of a flow, it's really that all cores can talk to a DRAM centrally.
Yeah, I'm not sure if you mean something specific by centrally, but you're able to pull data.
As opposed to DRAM bank that I can parallelly, in parallel or in some segmented fashion, read and write.
Yeah, the way I think of it is you kind of, again, you're able to have every core can read from DRAM, but you want to minimize that so you have
the central memory flow. Okay, got it.
Yeah. So it's kind of like a coarse grain reconfigurable architecture. Again, you're really trying to utilize the SRAM bandwidth instead of DRAM, so you can get around that DRAM memory bandwidth bottleneck. And that's kind of our answer to HBM, right? So we want to use that SRAM as much as possible.
I will switch quickly to the last part, which is resources from CMC microsystem and how to get started with the board. So I'm going to share my screen and show you the resources. So this is the main page for our Edge AI offering that I presented in my slides, enabling users to build, optimize, and deploy their AI application, and these are different various platforms. If you click on each of these one, you can get more details about the available resources. For example, this one is the FPGA GPU clusters, and this is the available resources, how to access it and how to use it. Since our topic today is about Tenstorrent Grayskull, so if you click on Tenstorrent Grayskull, you have all the information here, including datasheet and how to connect with me to have additional support. We have also a getting started tutorial on how to access it. So basically, we use CatPass, and CatPass is a tool from CMC that allow you to securely connect to our infrastructure. So basically, you use your registered CMC emails, and once you are connected, you will have access to the IP address of the server. You can just SSH to it by copying it from here, using your username. You can SSH to it. You can then interact with the board using simply the terminal, or you can forward the whole traffic to your Visual ST code environment, similarly to what Tom demonstrated today. So basically, using terminal, you can activate the environment. We have an environment for the TT-BUDA. You can run TT-SMI. This is similar to NVIDIA SMI to show you the available cards on the servers and their status. And then you can simply get started with the demos that Tenstorrent is making available. For example, the PyTorch ResNet that is available. You can just issue this command, Python PyTorch ResNet.py, to execute inference on the server using your SSH connection. And you can also run Jupyter Notebook by forwarding traffic to your local browser, and you can then interact with more advanced Jupyter Notebook demonstration. I have recorded a simple demo here demonstrating all these steps. So basically, you use CatPass to connect to our infrastructure. Once you are connected, you will have access to these resources. For example, here, there are various servers available to you. The one that is available from Tenstorrent is called AI Jupyter Tenstorrent. Once you are connected to that, you have access to the IP address of the server. Then you can just SSH to the server using your username. And then you can start interacting with the board. You could just issue LSPCI to see the available accelerator. Tenstorrent made available 2 cards for users, so you can use one of those. And this is TT-SMI, which is like similar to NVIDIA SMI, to show you the available cards and their status. So you can run inference using terminal here. For example, here, the example that Tenstorrent made available show you all the steps, the debugging steps that the scripts go through in order to perform inference, including all the optimization and all the steps to map the deep neural network to the underlying hardware. And you can also, as I mentioned, run Jupyter Notebook by just forwarding traffic to your local machine, and you can have access to the advanced use cases here, as shown in this demo. So you can double-click each one of these Jupyter Notebook and follow the instructions and learn about the different steps. For example, this is how to run a CV models using ResNet. And basically, you go through the steps, and then you can display the results and read the different messages from the board. For this example, for example, step 11, it prints and evaluate the output of the model, which is a tiger in this case. So this is very brief demo on how to access the resources and run inference. And if you have any additional questions,
you have a fabric. You have an ability to bring an iStream through the programming of the baby RISC-Vs, right? And then you can those are programmed from DRAM. Is that correct? So the loading of So if you want to temporarily time multiplex, then you would have to go back to DRAM. Is that correct?
Yeah, so that's kind of the big trade-off with temporal and spatial execution model. So you want to, again, it's all about tuning the ratio. So you
No,
train.
I understand the optimization. I'm just trying to understand how it works. So if I want to do that, then what I would have to do is load it, hopefully in parallel. Well, this is the question. In parallel, I want to be executing somewhere else while I'm time multiplexing in some other place, right? And then having. So one other question. So any graph has a theoretical max, right? So if you sort of say, hey, there's a graph. Average operator takes whatever time you want to give it, and then everything else above that is overhead, right? Interconnect overhead, DRAM overhead, all that stuff. In the tool, can you get the theoretical max and then sort of understand sort of how close you're getting to the theoretical, efficiency? Because I think that's sort of interesting to look at, especially relative to NVIDIA or other slice, kind of time slicing architectures, or even what's coming out with Dell and other people from. Do you understand what I'm saying? Because the graph should have a natural advantage relative from a theoretical max point of view.
Yeah, in Perf Analyzer, you can see estimates, say of the utilization. So that's like the MatMul utilization. And you can also compare the estimates against the measured kernel cycles using the full bandwidth constraints.
Types of things. That one technique is what you just talked about, but if there were others, it would be good to have sort of a, I don't know, at this point it's not a mathematical optimization, but rules of thumb.
Yeah.
That people can use that sort of start getting them going in this direction, because otherwise it's a very daunting, you can't look at these graph pictures because they're, it kind of gets useless very quickly. And, God knows what's running somewhere. And I mean, we can look at low-level statistics, performance statistics about, what's being overloaded or not. I don't know what you do with that. So it's sort of like you have to kind of seemingly take a top-down view and then sort of think about, of course, implicit parallelism, but the only way you can think about parallelism is some underlying architecture in mind, at a higher level. So just something to think about is maybe some rules of thumb that might be useful. Thanks.
Yeah, I definitely hear that ask, and like I selfishly really want that guide as well. And I know our engineering team is working kind of day and night on that problem, and I'd love to be able to take transfer that knowledge from their heads to some guide for you and the rest of the developer community.
That's what ChatGPT does, right? Never mind.
Yeah. But this is a great discussion because there are some models that are already optimized for the board and can be commercially deployed out of the box. And Raul, the topic that you brought is very interesting because I see a trend of supporting large language model on a very small edge platform. And this can be a problem where you have a large model and you try to fit it on a small design, a small architecture, or small chip. And I think this is an optimization problem, optimization and mapping problem. And also, if you can shrink these models also to fit within a small power budget, small memory footprint, is also another direction. So it's a multi-dimension problem, and it's a good research problem, research and development problem. I am sure Tenstorrent is working hard to make more large language model, especially for generative AI at the edge. That can be of a very good commercial use case to generate value and implement new applications. Please go ahead.
Yeah, sorry, just in that case, I can point you to the TT-Metalium or TT-Metal repo. So all this development's happening in public. And we have, for example, Falcon 7B you can run on the E150. So I can point you to that implementation. You can look at some of the tricks that our engineering team has done.
Yeah, maybe I'll just add one more to what you said. Yeah, I mean, in terms of interesting directions. So there's one interesting direction on how do you get I'll say more minimal models that are more appropriate for your application in form factors of interest, especially where power or price is an issue, and especially in the embedded world. But the other interesting direction to me is private data. So private data and connected to LangChain flows, and then the performance metric starts moving in an interesting way to, you know, more traditional scalar database connecting to graph engines, and you know, so you need kind of big RISC-Vs for that, which I know Tenstorrent's working on. And you need big processors. RISC-V would be the open source version of it. But those flows, I think, become very interesting because they're not, you know, they stress the combination of scalar processing and graph processing. So, all right. Well, thank you very much. Appreciate it.
Okay, guys. Thank you very much for attending today. I would like to thank again our guest speaker, Tom, for his presentation and for his continuous support to the Tenstorrent community at CMC Microsystem. The recording will be available early next week. And for more additional interaction, please reach out to me or to Tom. Thank you very much and have a wonderful day.
Thanks, Yassine.
Bye-bye.
Bye.